In this video, we'll solve another separable differential equation. Here I have dy dx is y squared minus 1 over x, and the fact that x is appearing in the denominator here suggests that x should never be 0. So we're probably going to be solving this equation either for positive x or negative x on a particular interval where x is not 0. It's pretty easy to separate this. If I divide by y squared minus 1, I'll have 1 over that on the left side, and on the right side I'll still have 1 over x. I then separate the differential, moving the dx over, and notice by doing this I'm assuming now that y, the value of the function, never takes 1 or minus 1, because that would make that denominator 0, and we should take note of that at this point. So now we're ready to integrate. On the left side we'll integrate this expression involving y, on the right side just 1 over x dx. The left side will require partial fractions. It's y squared minus 1. That factors into y minus 1 times y plus 1. That's why we weren't allowed to have these values of 1 and negative 1 in our solution. This breaks into two terms, y minus 1 and y plus 1. And there will be numerators in the top and bottom, constants a and b. We need to figure out what a and b are. Because this is distinct linear factors, we can use the cover-up method to find a and b. If you plug in 1 into the rational expression and cover up y minus 1, you'll have 1/2. That tells you 1/2 goes there. And if you cover up this one and plug in minus 1, because it makes that factor 0, you'll get negative 1/2, and there's the partial fractions decomposition. So we really just need to integrate 1/2 times y minus 1 in the denominator minus 1/2 times 1 over y plus 1. On the right hand side we still have that integral of 1 over x. So let's go ahead and do it now. Everything is involving logarithms. And a constant for integration appears at the end. So this gives us the solution to the differential equation. Right now it's implicitly given. We haven't solved for y by any means, but there's no derivatives anymore, and this expresses a relationship between x and y in order to satisfy this differential equation above. We might double both sides to get rid of the 1/2, and when I do that I get 2 times the log of x over here, plus twice my original constant. I'll call that c1. The left side is a difference of logs, so that becomes their log of their quotient. The right side becomes log of x squared. I can raise that 2, the coefficient of the log, up to a power. Notice I don't need absolute values anymore. That's nice, because it will be positive. And then plus our constant. And so this is almost ready to solve for y. What I need to do now is to exponentiate both sides. Raise both, use both as a power of e, and when I do that here on the left side I'll have e to the log of that rational stuff. And be careful here when you do it to the right side. I've highlighted the constant here. That's all part of the exponent. And that's important because when I rewrite this, the e to the log will just give me what I'm taking the log of, so just that. And when I rewrite it on the right hand side I'll have e to the log of x squared, but now it will be times e to the c. If I'm adding exponents, I multiply bases together. If we simplify that, we're going to have a constant part. E to the c, I'll call a, and so we'll have some constant a. An exponential is always positive, so it's going to be just some positive number here. A is any positive real number. And then e to the log of x squared is just x squared. And so the absolute value of this expression is equal to a times x squared. If I want to get rid of the absolute value, that means the right side could be positive or negative that amount. So we now have two choices. And that just means that y is equal to b times x squared, where b is plus or minus a. In other words, b is just some non-zero constant now. So at this point we have a formula for the solution to the differential equation. It's implicit because I haven't solved for y, but it's pretty close to being solved for y, and b here is some arbitrary non-zero real number. So here was the original differential equation. We found the general solution implicitly given by this formula that we just had on the previous slide. And let's see if we can solve this for y. The first thing you might do is to multiply both sides by that denominator. So we'll have y plus 1 over here. Let's expand everything out. So I have bx squared times y plus bx squared. And then I'm going to bring the terms that have y in it, in this case this term, over to the other side. And the terms that don't, in this case the minus 1, over to the right side. And when I do that, I'll have this expression. Let's factor the y out of the left side. And then we're going to divide by the factor of 1 minus bx squared to solve for y. And so right now I have an explicit general solution. Y is equal to this irrational expression where b is some non-zero constant. Now remember, we assumed at some point that y is not equal to 1 and y is not equal to minus 1. And we should consider whether or not those were solutions as well. Our analysis on the previous slide gave us this general form under the assumption that it wasn't those two values, but we should consider those separately. But both are in fact solutions. If you take y equal to 1, that occurs in fact when b is equal to 0. Both these terms will go away and we'll have y equal to 1. And if you take y equal to 1, you plug it into the differential equation here, you'll have 1 minus 1, that'll be 0 on the right side. And the derivative of the constantly 1 function is also 0, so it will satisfy the differential equation. If you take y to be negative 1, square it and subtract from 1, you'll have 0 here, and its derivative, because it's constant, will also be 0, so that's a solution as well. Solutions that pop up, these kind of one-off solutions that occur just from certain exceptional cases, are called singular solutions. So what we have here is the general solution, and then we have these two singular solutions that are also possible solutions. They're probably not the ones you're interested in applications because they're just boring constant functions. Probably what you're interested in is somewhere in the general solution.